Today our concept, thin linear wire antennas. Thin linear wire antennas. This is the second unit of antenna and wave propagation. Thin linear wire antennas. Coming to the picture. In our first unit, we have studied the fundamentals of antennas, that is the parameters of the antennas. Right now, in our second unit, thin linear wire antennas. Basically, the electric charges are the source of the electromagnetic field. Electric charges are electric charges are sources of electromagnetic field. When these sources are time varying, the electromagnetic waves propagate away from the sources and radiation takes place. Okay, so radiation can be considered as the process of transmitting energy. Radiation can be considered as process of transmitting electric energy. Electric energy. Again, coming to the picture, when the sources are time varying, the electromagnetic waves propagate away from the sources and the radiation takes place. Actually, basically, by considering a off-wave dipole, the structure is like this. So the source is fed to the center of the antenna. So when this source is a time varying, when these source are time varying, the electromagnetic waves propagate away from the sources and radiation takes place. So radiation can be considered as process of transmitting electrical energy into transmitting electric energy into electromagnetic waves. So the radiation of waves into space is effectively achieved with the help of conducting or dielectric structures of structures called antenna. So this is the antenna. Again, the process and the radiation of waves into free space, the radiation of waves into free space is effectively achieved with the help of some conducting or dielectric structures, which is called an antenna or a radiator. So in sometimes antenna is also called a radiator. Antenna is also called a radiator. So an antenna is means of radiating or receiving the electromagnetic waves. So here in this picture we call it as a radiating, and if some other receiving antenna is also receiver is also is there. So another of a dipole is fed at the receiver antenna, so that this antenna is capable of receiving electromagnetic waves. So an antenna is a means of radiating or receiving the electromagnetic waves. So an antenna may be used either for transmitting or receiving electromagnetic energy. Alternatively, an antenna can be defined as a transition or matching unit between the sources and waves in spaces. So, in the design of antenna systems, we must consider important requirements such as antenna pattern. Next one, the total radiated power, okay, and input impedance of the radiator, the radiation efficiency, and so on. So the direct solution for these requirements can be obtained by solving Maxwell's equations with the appropriate boundary conditions. Total radiated power, input impedance, input impedance of the radiator, and efficiency of the antenna, efficiency of the antenna. So in order to analyze the antenna system, we must consider these important requirements of the antenna, so that in order to observe the antenna conditions. So these requirements can be obtained by solving a Maxwell's equation, solving Maxwell's equations with appropriate boundary conditions of the radiator at infinity levels also. It is observed that most of the antenna configurations are complicated. Most of the antenna configurations are complicated. So this direct approach is suitable for certain types of antennas. Uh, so again, we look at into the sources of radiation and the radiation mechanism. We will look at once sources of radiation and radiation mechanism. Sources of radiation and radiation mechanism. Actually, and this is the first unit topic. Already we have covered this one. Again, once we look at into this. Even after being the basic source of the radiation of electric charge, radiates under certain conditions only. If the charge is stationary, the current is not created, hence there is no radiation. Look at a static charge is like this. A static charge. If the charge is stationary, the current is not created, and hence there is no radiation from this charge. If an electric charge is moving with an uniform velocity along a straight way, and look at into this one. If you feel this is a straight way, a uniform velocity is a velocity along a straight line with a velocity v along a straight way with a infinite length, then also there is no radiation. Then also there is no radiation. Of course, you may assign some names here. This is the figure 1. This one is a 2. Okay. Now the question arises how the radiation takes place. To explain this phenomenon, let us establish a relation between a current and a charge for an electromagnetic radiation. Let us consider that a pulse of electric charge moves along a straight conductor in z direction. So coming to the same picture, a conductor is like this. Okay, a pulse of charge, a pulse of charge in a z direction. So this is a z direction. Let us consider a pulse of electric charges moves along a straight conductor in z direction. Now note that QL, Q suffix L, be the charge per unit length expressed in coulombs per meter. Coulomb per meter. Please observe this pulse of electric charge moves along a conductor in z direction. Here QL is coulombs per unit length expressed in coulomb per meter. Such a moving charge constitutes a momentary current. Such a charge Q charges constitutes a momentary current. I is given by I equal to Q suffix L into dz by dt. This is ampere. Let L be the length of the pulse measured along the conductor. So we get I into L equal to Q suffix L into L dz by dt. This is ampere per meter. Let dz by dt is nothing but velocity v expressed in meter per second. Expressed in meters per second. Here we can write like this. So I into length equal to Q suffix L into capital L into V. V is nothing but dz by dt. The term Q suffix L into L is nothing but the total charge of the pulse. So we can rewrite the equation as I into L equal to Q, total charge into V. Differentiating the above equation, suppose this is one equation, differentiating the above equation, I into dl by dt equal to q into dv by dt. Here dv by dt is nothing but a acceleration of charge. So here we get like this, I equal to, sorry, this is q into a. Here a is nothing but acceleration of charge, which is in meters per second scale. So this is the another equation. So this is the basic continuity equation relating charge and current together. Not only this, but it is also a fundamental relation of electromagnetic radiations. So from this equation we conclude that with a time varying current or accelerated or deaccelerated charge, electromagnetic radiations are produced. Depending upon the application, current and charge are mentioned for time harmonic applications. Okay, so this is the basic continuity equation in electromagnetic wave radiators. So coming to the next one, potential functions and electromagnetic field. Next concept, potential functions and potential functions and electromagnetic. Yes. Potential functions and electromagnetic fields. Right. Now coming to the picture, in just now we have discussed the continuity equation. Now, in case of electrostatic field or the steady state magnetic field, the electric field or the magnetic field can be obtained easily by first setting the potentials in terms of charges or currents. By setting charges and currents, we can easily obtain electric field or the magnetic field. In case electromagnetic field, the similar procedure may follow. First of all, the potentials are obtained in terms of charges or currents, and the electric and magnetic fields are obtained from these potentials. For obtaining the potentials of the for the electromagnetic field, there are different approaches. In last session, we just derived for a conducting continuous conducting wire only. Now, now we are finding for electromagnetic field for different approaches for obtaining the potentials for electromagnetic field. So, for obtaining the electromagnetic field, there are different approaches. In the first approaches, by using a trial and error method, the potentials for the electric and magnetic fields are generated. Then it is shown that these potentials satisfy Maxwell's equations. This approach is called heuristic approach. Again, I am by using trial and error method, the potentials for electric and magnetic fields are generated. After getting these values, then these values must satisfy Maxwell's conditions, Maxwell's equations. This approach is what we call heuristic approach. Heuristic approach. The second approach is to start with Maxwell's equations and then derive the differential equations that the potentials satisfy. The third approach is to obtain directly the solutions of the derived differential equations for the potentials. So by three methods, now this is the first one. What is the second method is to start with Maxwell's equation and then derive the differential equations and then derive differential equations, then satisfy the potentials. This is the second one. And the third one is to obtain directly the solutions of the derived differential equations of the, this is the direct solution, directly obtain the solutions. So when we analysis in detail, we can understood one by one right now. Right now, please look at into the heuristic approach. No, heuristic approach. Heuristic approach. What this indicates? This is a heuristic approach is a trial and error method, as discussed just now. In this approach, first we have obtained the potentials for the electric and magnetic fields. Okay, so consider a uniform volume charge. Suppose this is an volume. So this is a volume, uniform volume charge, density. So rho V, rho V over the given volume as shown in the figure, as shown here. Consider the differential volume, that is differential volume is represented by dV dash, dV hyphen dV dash at a point distance from the origin. This is O, this is the origin at a point distance from R dash. Okay, where the charge density is rho V, rho V with a distance of R dash. Then the scalar electric potential V at a point P can be expressed in terms of a static charge distribution. All of this is an assumption. Suppose at a point P, we have to calculate the scalar electric potential V at a point P. Then it is expressed as a static current distribution, like V of R. So this is R dash, this is R, and the distance between O and P is R. Okay, V of R equal to integral of the volume, surface volume V, rho V r dash into dV by 4 pi epsilon r. Then the fundamental electric field can be obtained by finding the gradient of a scalar potential V. So that is E scalar potential E equal to minus del into V. This is, we know. Similarly, for a steady magnetic field in a homogeneous medium, the vector magnetic potential A bar can be expressed in terms of current distribution, which is constant with time. That is A bar of R. This is a magnetic potential. This is a scalar electric field potential. So A of R equal to, again, integral V mu J of R dash by 4 pi capital R dV dash. Then the fundamental magnetic field can be obtained by finding the curl of the vector magnetic potential A bar. We know from the Maxwell's equations, B bar equal to del cross A bar, that is mu into H bar equal to del cross A bar. We know these equations. By keeping these equations in mind, the potential equations, the potentials given by equations like electric field potential and magnetic field potentials represents for the static, electric and magnetic fields respectively, where the charge and current distributions do not vary with time, but the charge and current distributions producing electromagnetic field vary with respect to time. So thus, for time varying fields, we must modify the potentials represented by equation, the above equations, for time variations. That is, just the above equations can be represented as V of r dash comma t equal to 1 by 4 pi epsilon into integral V rho V, sorry, this is rho V r dash comma t. It is a time varying. It is a function of time into dv dash. In the same way, a magnetic potential equal to mu by 4 pi into integral V j r dash, j is a function of t by r into dv dash, where here r can be represented like this. So the above two equations, suppose this is a 3 and this is a 4. So the above equations, it is clear that the potentials vary instantaneously as the charge or current distribution varies. But in general, the velocity of electromagnetic field propagating through any homogeneous medium can be described in terms of mu and epsilon. So here V velocity V can be represented V equal to 1 by root of mu into epsilon. So this equation, it is clear that the potentials are delayed or retarded by some time. So hence the potentials are called retarded potentials. The potentials are called retarded potentials. So why it is retarded potentials? Retarded means time vary. So when the potential at any point is not due to the value of charge density, the same distance point at the same instant, but to its value at some previous instant as the electromagnetic wave propagates at a finite velocity. So for a time delay, for a time delay, uh, the retarded can be represented by T can be replaced by T minus R by V. T minus R by V. So we can replace these equations. You can replace this term with this term so that it is a retarded one. So retarded potentials. So the fields obtained from retarded potentials are related to each other through the Maxwell's equations. So this is because the current and charge distributions are not independent but related to each other through the continuity equation. So this is the Maxwell's heuristic approach by using trial and error method by assuming some equation parameters, and we assign to these equations to Maxwell's approach, Maxwell's equations. So this is what we call a heuristic approach. Here the main concept is retarded potential. That is, here the continuity equation is delayed. The time delayed is T minus R by V. Students, you may follow these sections. If anyone is having doubts in particular area, particular concept, you please mention that one. For that one, I try to make another videos. Thank you. Thank you very much.